Okay, part 2 of integration by parts. We are going to make sense of this and make it easy. It will be easier than it was before. So I showed you in the last video in part 1, kind of this wild formula and blah, 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 all these U's and V's and highlights. I want to show you the easy way how to do it. So key is that we showed that this integral with some hard U and V work gave us this thing right here. I want to show you a much, much faster way to do it. So, sometimes people call this tabular method. I sometimes like to call it dir and int. So, dir for derivative and int for integrate. So, I'm just going to show you how to do it with this first one. Maybe explain a little bit. But I have 2 parts to this thing. I'm going to call the first part x, and this is the highlight colors are totally different from what I was doing before. And the second part, cosine, undo. The second part, cosine x. So that's why we call it integration by parts, because we got 2 different parts. So I am going to let the dir side, be x. So maybe I'll write x. And I'm going to take the other part. So that is this. It is yellow. And then I'm going to take the other side, the cosine x. Come on, get that. There we go. Cosine of x. And I don't even bother writing the dx. It's unnecessary. So what I do is I break it into 2 parts. And when I say dir, we're going to put that on the dir side. And we're going to derive it. So let's take the derivative of that. What's the derivative of x? It is 1. And then I'm going to do another layer of derivatives, and we get 0. Typically, and there's other scenarios when we're doing this dir and int, this integration by parts, tabular method, we dir until we get to 0. Next thing we need to do on the other side is integrate the same number of times. So I got to integrate cosine x. Well, let's think in our head. That goes to a positive sine x. And then since I had another layer over here, I'm going to integrate again. That gives us a negative cosine x. Now, what we do is we go diagonally. We're going to go like this and like this. And then that becomes multiplication. You may be like, what? Just roll with it. It is the easiest thing in the world once you get the hang of it. So I make this plus and I make this minus. The plus and minus is that every time we alternate signs, every time we go do an arrow, each arrow, we will alternate signs. So for example, if there were 3 arrows, I would go plus, then minus, then the next one will be plus. And then here's where we go, or here's what we get from that. I simply go and I take the product along the arrows. So it gives me x times sine x. So I'm going to write x times sine x. And then I take this product. And what's that give me? A minus and a minus, a double negative. So that's plus, and then cosine x. What I want to do is zoom out just a little bit, and I want you to see that that's exactly what I have in this box right here. X sine x plus cosine x. And I didn't have to do any of this UV stuff. I didn't have to color code things, right? So I just pick a dir side, pick an int side, or I take the rest of it, it's inside, and then I do this process, and it'll give me that answer without having to sort through all these U's and V's. So I want to quickly show you why this works. Let's take the integral of u dv minus, or is equal to, u times v minus the integral of v du. That's the formula. I want to just show you that this dir and int thing fits the formula. I'm going to take a dir side and an int side. My dir side is going to be u. My int side is going to be dv. I will highlight in the same way. Boink, boink, and boink, boink. Now, what are we going to do? We're going to dir this once. What does that become? Du. We're going to int this once. That becomes v. And then I'm actually going to integrate one more side on this right side. What's the integral of v? Well, it's exactly what I just said. It's the integral of v. Now watch what happens when I do my multiplication. That one gets plus because it's the first arrow, and this one gets minus because it's the next arrow. What do I get? I'm trying to show you that this right here lines up, or that the integration by parts process lines up with this formula. So I can take this side if I do my dir and int columns tabular method. What do I get? The first product is u times v. And then what's the next one? I get my minus from that right there. So minus. And then I'm just going to write it as the integral. I'm going to write this piece first right here. Integral of v. Make that look like a v. And then this, which is times du. So now I want you to see that this is what I have on this side. So structurally, it just makes the u's and v's for us, and it makes it so that we don't have to think about them. So let me do another example here, because they get easier as we go along. All right, so here we go. Integral of x cubed times sine of x. So, with a dx. Now, what am I going to do? I'm definitely 100% doing this in tabular method, in dir and int, because otherwise it's going to be crazy. Dir side and int side. You may say, how do I choose what is the dir side and what is the int side? Well, we want something on the dir side that's going to go away. Notice here I got to 0, and that's why I stopped. So, if I were to put sine x on the dir side, it would just keep deriving, and it would go for forever, because sine drives to cosine, and it keeps going on in a long chain. And then if I were to put the x cubed on the int side, then again, these powers would be increasing. So I definitely want the x cubed on the dir side. Oh, come on. X cubed. And then I'm going to put the rest of it, sine x, on the inside. Now, here's what we do. In the previous one, I had 3 layers. I'm going to derive until the x cubed goes away. 3x squared, 6x, 6, and 0. Now what I need to do is do all the ints. All right, so let's just be really careful with our positives and negatives. Sine derives to a negative cosine x. Negative cosine keeps the negative and becomes a sine x. Then this gets a double negative and becomes a positive cosine x. And then I do one more, and it becomes it stays positive, and we get a sine x. And then I do the same thing that we did before. I do these diagonal arrows like this, and I just alternate signs. Plus, minus, plus, minus. And then I can just write out all of these products. I take x cubed, and I multiply it by this piece over here. So what do I get? Minus x cubed times cosine x. So I got the first set of arrows. Then this one. Look, I get a double negative because there's a negative and a negative there. So it becomes plus, and then I get 3x squared times sine x. And then the next arrow, make sure you're alternating signs, plus, minus. We're on a plus again. So this gives me 6x times cosine x. And then the last one is minus 6 sine x. And that's it. That's integration by parts. This, if I was using u's and v's, would take forever. Like if I was doing it on a sheet of paper, it would take an entire sheet of paper, and it would be so terrible. So tabular method is really, really, really nice. Do we have time? I think we do have time for one more. All right, so the next one we're going to do is going to be the integral of x squared times e to the 3x with the dx. I want to back up a moment and talk about how we know we need to use integration by parts with this. If you go to the very top of what we started with originally, I had all these integrals that had u sub. That's because the u sub worked. Remember, u sub wouldn't have worked here. So if I come down to this example that we did here, x cubed with a sine x, I can't do a u and a du because it's not going to work. So this is where integration by parts can solve problems that we couldn't do before. So coming down to this one, I'm going to try to do some integration here. But you can see if I make u equal to 3x, I'm not going to get an x squared out of a du. So what I'm going to do is try dir and int. So let's go dir, let's go int. Which one are we going to put on the dir side? We're going to do x squared, and I'm going to derive it until it goes away. 2x, 2, and 0. what am I going to put on the inside? E to the 3x. Now, when I integrate e to the, it gives me an e to the, so I'll write e to the 3x. And I'm going to put a 1/3 there to balance a little bit of chain rule. And then I'm going to get e to the 3x again, and I'm going to get a 1/9 out front. And then the last row, I'm going to get e to the 3x, because I want to have 4 rows in each of them. And I'm going to get a 1/27. So from here, I do my diagonal arrows, and I go plus, minus, plus. And then I just multiply along the diagonals. So what do I get? First one is 1/3. I'm going to put that out front. X squared e to the 3x. And then I'm going to get minus, and I'm going to simplify my fractions to be a 2 in the top and a 9 in the bottom. And then I'm going to write my x, and then I'm going to write my e to the 3x. So I put the 2, and then over the 9, and then the x, and then the e to the 3x. You could write it in a way that works well for you. I just like having that fraction out front. And the last term is going to give me plus 2/27 times e to the 3x. And I may have forgotten in the last one, but I want to include that plus c. So that's that integration. What do I want to say? I hope that when I did this little bit of work right here, it connected this whole idea of tabular method to integration by parts. And remember, like, we started from scratch. I didn't assume anything other than like rules that we've already done in calculus. So I just did some product rule, right? I hope you're convinced that this has to be true based on this work that we did. And I hope you're convinced that that having to be true lines up with being able to do this tabular method, which is what we did right here. And then it's a little bit more work to explain or to connect this this formula to being able to do multiple rows of tabular method, but it works, I promise you. And this technique just becomes so powerful and so useful and so important as we move forward, and it opens up so many doors in calculus for able to integrate things that we wouldn't be able to integrate otherwise. And I hope this helps make some sense of it. So see you next time. Bye.